Hey everyone, and welcome to this explainer. When we think about ocular inflammation, we usually just write it off as a pesky, painful symptom, right? A red, irritated eye that we just want to quickly soothe with some drops. But today, we're going to reframe that entirely. We're going to look at inflammation not as an annoyance, but as a fascinating, highly orchestrated, microscopic biological battle plan. Your body is actually executing a profound, ancient strategy to save your vision.
Okay, let's dive into this. Why exactly does an injured eye turn red, swell up, and throb with all that pain? Well, we are going to look way past the visible discomfort your patient might be feeling to reveal the perfectly designed microscopic alarm system at work right beneath the surface. It's a whole system of chemical tripwires, protein cascades, and cellular cavalry.
So, here's our roadmap for today. We're going to start with the initial spark of inflammation, move right into sounding the chemical alarms, explore the ancient complement system, track our cellular first responders, and finally look at what happens when this incredible defense actually becomes a disease.
All right, kicking things off with part one, the spark of inflammation, moving from a noxious stimulus to a visible reaction.
So when a noxious stimulus hits, and that could be anything from an infectious bacteria to a physical trauma or chemical burn, your body enters this acute shock phase, which is characterized by 5 classic cardinal signs. First, we've got rubor or redness, and calor, which is heat. Biologically, both of these are caused by a massive, rapid increase in blood flow right to the site. Then we have tumor or swelling, dolor, which is pain, and functiolesa, meaning a loss of function. These last 3, they're caused by the exudation, literally the pouring out of fluid and irritating chemicals into the surrounding tissue. And this brilliantly illustrates the sheer contrast between the macro and micro worlds. On the left, you're seeing what the patient and the clinician see, which is a painful corneal ulcer with a purulent exudate, a notoriously red and swollen eye. But on the right, look at what the pathologist sees under the microscope. See those tiny dark dots? Those are actual white blood cells, specifically polymorphonuclear leukocytes, rushing to the site and sticking to the corneal endothelium to fight off the threat. Moving on to part 2, sounding the chemical alarm, those invisible triggers that mobilize the body. Now, to understand how those cells know exactly where to go, we have to look at the sheer speed of the body's response because it's honestly incredible. Immediately after an injury, there is this fascinating 5-minute window where the arterioles briefly contract, just 5 minutes. But right after that, they gradually relax and dilate. This dilation is driven by chemical mediators and drastically increases blood flow to the area. Interestingly, as fluid leaks out into your tissues, the blood inside the vessels actually gets hyperviscous and sluggish. So to prevent widespread clotting in this thick, sludgy blood, your local mast cells release heparin. So, what exactly are these chemical mediators opening the floodgates? First up is histamine. It's locked away in the granules of your mast cells, just waiting to be released to cause immediate vasodilation and increased vascular permeability. Then you've got prostaglandins, produced by the cyclooxygenase pathway, which drive both the vasodilation and that intense pain and fever we associate with inflammation. Finally, you have kinins, derived straight from your blood plasma, forcing smooth muscle contraction and ramping up the pain even further. These are literally your body's critical chemical alarms.
Which brings us to part 3, the ancient complement system, a literal billion-year-old defense network.
1 billion. Think about that for a second. Those chemical alarms we just talked about, they awaken a complex cascade of almost 60 proteins in your blood plasma. And I absolutely have to emphasize the staggering ancientness of this network. The complement system is so utterly vital to biological survival that evolution has preserved it across species for over 1 billion years. It's an incredibly precise, lethal mechanism perfected over eons. Now, what's really interesting about this slide is the sheer variety of jobs this billion-year-old network handles. I mean, it doesn't just do one thing. These proteins label or opsonize foreign antigens so your phagocytes can easily spot and eat them. They recruit and activate nearby white blood cells, they clear out spent antigen-antibody immune complexes, and most aggressively, they directly kill invading bacteria through cytosis, literally breaking the invading cells apart. The way the complement system achieves all this is through a really strict cascade. There are 3 primary routes here: the classical, the lectin, and the alternative pathways. But notice how they all funnel down and converge on one major hub, which is the activation of C3. Cleaving C3 produces C3a, an anaphylactotoxin that triggers a massive pro-inflammatory response, and C3b,
which physically coats and opsonizes foreign surfaces.
And here is the ultimate weapon at the end of this complement cascade: the membrane attack complex, or MAC for short. It's made up of 5 terminal proteins, C5b, C6, C7, C8, and multiple molecules of C9. The MAC operates with just brutal efficiency. It physically embeds itself right into the membrane of an invading pathogen and punches a microscopic hole straight through it, causing the cell to lyse and tear apart. It's literally a molecular drill designed to destroy threats. All right, part 4, the cellular first responders, the arrival of the microscopic cavalry. So, with the chemical alarms ringing and the complement system activated, the stage is set for the physical cells to arrive. Meet your first line of cellular defense: polymorphonuclear leukocytes, or PMNs. Born right in your bone marrow, these cells are the most numerous of your circulating white blood cells, making up 50% to 70% of the total. And you can easily spot them under a microscope by their highly distinct, segmented, multi-lobed nuclei. Let's move to and see how this builds, because tracking their physical journey is wild. How does a PMN actually get out of the bloodstream and into your injured eye? Well, first is margination. The cells start sticking momentarily, then tightly to the blood vessel walls. Next up is emigration, or emprypalosis. Using active amoeboid movement, the PMN literally squeezes itself through the tiny junctions between endothelial cells, a whole process that takes about 2 to 12 minutes. Finally, chemotaxis. Once they're outside the vessel, the PMN follows the chemical trail left by the complement system, moving relentlessly along a gradient straight to the injury site.
And once they arrive, PMNs absolutely do not take prisoners. They engulf the noxious material through phagocytosis, then they unleash brutal chemical warfare. They produce highly reactive metabolites like hydrogen peroxide, which converts into hypochlorous acid to just obliterate microbes. They also dump lysosomal digestive enzymes onto the threat. And because this work is so intense and destructive, PMNs are end cells. They die after just a few days, liberating their enzymes and leaving behind a purulent exudate, which we all commonly recognize as pus.
Which leads us to our final section, part 5, when defense becomes disease, the double-edged sword of immunity.
Now we've got to pivot to a really crucial, slightly darker aspect of this explainer. What happens when this incredibly destructive billion-year-old system misfires? So the crucial point is this: the complement system is so deadly that almost half of its actual biological job is simply regulating itself so it doesn't accidentally destroy your own eye. In a normal eye, complement regulators precisely protect your healthy tissue from those hole-punching membrane attack complexes. But in a diseased eye, if there is a defect in that regulation, the system misfires. The complement proteins start opsonizing and lysing your own healthy native cells. We call these conditions complementopathies. And the consequences of these complementopathies are frankly devastating. Just look at the pathological evidence tying impaired complement regulation directly to major blinding diseases. In age-related macular degeneration, we find accumulations of that MAC complex C5b9 literally destroying the drusen, retinal pigment epithelium, and choroid. In glaucoma, that exact same MAC is found attacking the delicate ganglion cell layer. In uveitis, those potent complement anaphylatoxins C3a and C5a are found just flooding the aqueous humor. The very system meant to save the eye is actively tearing it apart.
Which leaves us with a pretty profound realization, doesn't it? Inflammation and the complement cascade represent our oldest, most highly evolved biological shield. It's an absolute masterpiece of cellular and chemical engineering that keeps us alive every single day. But maintaining that delicate, miraculous balance is absolutely everything. Because what happens when that shield turns against us? It's life-altering. Thank you so much for joining me on this deep dive into the microscopic battlefield. Keep questioning, keep learning, and I'll catch you in the next explainer.